All right. So the next property is the fact that ice floats, which is, I mean, everybody knows probably that ice floats, but you probably never thought of that being a unique property. The thing is that typically solids, we teach you that this is chapter 2. This is chapter 2 chemistry. You learn solids are the most dense. Everything's really tightly packed. Liquids are less dense because they're flowing. And then gases are the least dense because the molecules are really far spread apart. So we're kind of lying to you a little bit because this is an exception to that rule. Solid water is less dense than liquid water. The particles are actually farther apart in ice than they are in liquid water. We're going to talk in a second about why. Water is actually the most dense at 4 degrees Celsius. At what temperature does it freeze? At 0 degrees Celsius. So something kind of unique happens to water when as water starts to cool. So imagine it's getting cold outside, you have a lake, it's winter time. As the water starts to cool, it actually gets more dense and it starts to sink. This is going to slow down the freezing process because what that's going to do is as that water sinks, it brings warmer water up from the bottom and it causes actually what's called turnover. This actually happens in the fall and the spring. It actually helps to stir up the water and move the nutrients around, but it prevents freezing for some time. Eventually, you are going to get some water on the surface that gets below 4 degrees and it's going to be somewhat less dense and it's going to freeze. But if ice was to sink, water would freeze lakes would freeze from the bottom up and everything would die. Instead, you end up with ice covering the surface, and when the ice covers the surface, it insulates everything underneath. So all the organisms living in the water, the plants and the fish and the algae and all those things, they don't freeze to death because the ice on the surface actually protects them. Now, it actually is also true, just a little tidbit, that like Arctic fish and things like that, they actually have something very similar to antifreeze in their blood. So they can actually be below freezing without the water in their cells freezing, which is kind of interesting. But the fact that ice floats means that it actually becomes an insulator. Now, why does ice float? So here's the reason why. This is why water is unique. Remember we talked about it being polar and how it makes hydrogen bonds. Typically, hydrogen bonds are very weak and they're being made and broken. So if you imagine I'm a water molecule, which means I'm kind of like this, right? I'm bent and I have my 2 arms sticking out. That means that if I form a hydrogen bond with another water molecule, I'm going to temporarily, let's say, lock with him. We're going to be stuck a certain distance apart because that hydrogen bond is going to hold us. It's sort of like shaking hands. I can't get any closer than that bond. But if I'm liquid water, that bond is going to form for a split second, then it's going to break, then I can slide close to him and get near somebody else. So as I make and break the hydrogen bonds, temporarily when the bond is formed, we're held apart. But when the bond breaks, we can slide close to each other. So the liquid molecules of water are sliding close to each other, and the hydrogen bonds, everywhere they're bonded, they're a little further apart. When it freezes, all those bonds lock in place. So that means you're going to get, if I show you here in this picture, you get, I didn't mean to do that. You get something like this, which is sort of a honeycomb. The water molecules are actually, because of the hydrogen bonds, it literally locks them farther apart. They can't slide anymore. And so liquid water takes up more space. This is why if you ever put your water bottle in the freezer so that your water will be cold and then you forget about it and it completely freezes, sometimes your water bottle won't stand up anymore. Your water bottle gets all bloated and stretched out because the ice takes up more space than the water, so there's not enough space. I know I've put sodas in the freezer to cool them faster and forgotten about them because I'm old and stuff like that. I come back a few hours later and the can is busted. It literally, because the aluminum doesn't stretch, the ice takes up more space than the soda did. There's not enough space and the can literally bursts open. So that's why that happens. And that is unusual. Most solids are more dense. If I was to melt aluminum and drop a solid piece of aluminum into the molten aluminum, it would sink to the bottom. Water is actually very unique. There aren't a lot of substances where the solid is less dense than the liquid form of the same substance. So, all right, last part, acids and bases. We already talked about this in the previous lecture, but just a quick reminder. So the thing with acids and bases is that, remember, water breaks up a little bit, a very, very little bit, into hydrogen and hydroxide ions. But it's such a tiny, tiny amount, it's almost imperceptible. It's not enough that you could even use it to conduct electricity. And in fact, in a mole of water, if you recall, I told you that it's about 1 × 10⁻⁷ hydrogen ions, and the same number, 1 × 10⁻⁷ hydroxide ions. And we could measure acids and bases pH scale, the pH of pure water is what? 7, right? So if we take the negative log of this, we get the pH of water is 7. And if we were to take the negative log of the hydroxides, it would also be 7. And they always add up to 14. So if something is becoming more acidic, what acids are, just a reminder, anything that gives up or increases the hydrogen concentration would go up. The OH, hydroxide, would go down. Those would be acids. And things that pick up hydrogens or increase the hydroxide concentration were bases. So in acids, the hydrogen concentration, just a reminder, would go up, but the pH itself would actually go down because it's the negative log. So 10 to the negative 7, it goes down to 10 to the negative 6, goes down to 10 to the negative 5. Technically, this is a bigger number than that, or that. The numbers are getting bigger. 10 to the negative 2, which is a pH of 2, would be that. So as the pH goes down, the hydrogen concentration, these numbers, the hydrogen concentration is actually getting bigger as the pH drops. So a pH of 2, a pH of 5, a pH of 7, etc. Anyway, but we talked about this in the previous lecture. The reason that I bring it up again, though, is number one, water allows acids and bases to form. But in addition to that, the other thing about water is that there are substances in your body called buffers. In chemistry, in AP chemistry, you learn a lot more about buffers. And here, you really just need to know the basic definition. But the problem is you don't want the pH in your body to change too drastically. If the pH goes really high or really low, you'll die. You'll go into a coma and die. So what prevents that from happening is buffers in your body and the water. So these buffers, what they do, it's sort of like, I don't know, and nobody probably pays cash anymore for anything, but if you go into some little stores, there'll be like a little tray here, and it's called like give a penny, take a penny. Like if you're short a couple cents, you can use the change from that to pay, and when somebody else gets change back, if they don't want it, they'll toss it into that. That's sort of like what a buffer is. A buffer is sort of a substance that sits there, and if your blood starts to become too acidic, something is giving up a lot of hydrogens in your blood, it'll pick up the extra hydrogens. And if your blood starts to become too basic, it'll give away extra hydrogens. And it'll keep the pH from changing. You have a lot of different buffers in your body. And again, in reality, there's a lot more to buffers than just that explanation. But for this class, that's really all you need to understand. Is that a buffer is a substance that has the ability to prevent pHs from changing. It doesn't necessarily mean it keeps the pH neutral. You may have areas of your body where the pH needs to stay at 9. So there's buffers there that will keep the pH at 9, that will pick up or release hydrogens to keep the pH there. So it doesn't necessarily mean it keeps something neutral, but it keeps the pH stable at whatever it's supposed to be. In your stomach, you want the pH right to be acidic. I think the pH in your stomach's like 2 or something. You make hydrochloric acid. Yeah. Your blood is about 7.4. I think your upper intestines are like 8.6 or something like that. So different areas of your body have different pHs. Buffers help to control those pHs. You can throw off the buffers. If you breathe into a paper bag, you will pass out. I don't recommend it. Because what you're going to do is you're going to increase the carbon dioxide. The more carbon dioxide you have, it pushes it this way and your blood starts to become acidic. Buffers will stop that if you're just running, if you're just jogging and you're making extra carbon dioxide. The buffers in your blood will stop the pH from changing. But I mean, if you force it and you breathe into a paper bag where you can't, you overcome the buffer, you'll pass out. Little kids will hold their breath till they pass out. There are some kids that are so obstinate, they're so angry, they're just like, I'm not gonna breathe, and they hold their breath. Basically, they'll pass out because it's their body's way of going, okay, well, you are gonna breathe, and as long as they don't hit their head when they fall, they're gonna go back to normal, because when they pass out, you're gonna breathe again. So buffers will prevent it. I mean, they're not infallible, but they will hopefully keep most things in a regular range. You had a question? Oh, alkaline water. I don't know if that's really a good thing or not. I've heard of that. I've heard that they talk about it being better for you, but I don't know. Neutral. Yeah, pure water is neutral. But then there's certain waters that have like minerals and things that may change the pH. Like, I don't know if what is it, Fiji or that really expensive. That, yeah, it's more expensive, or yeah, Boss or whatever. Comes in a glass bottle. Must be cool. But yeah, and the pH may be different. But yeah, I know that's a thing now. Is the alkaline water, and I don't know what their goal is with that. Because yeah, water is normally just neutral, so I'm not sure what they're going for. I don't know. They come up with all kinds of stuff. You don't have to know this specific example of carbonate. I just put it there as just one of the examples. In fact, I have a little table here just showing you. These are just some different systems. If you take anatomy, you may learn more about some of this stuff. Just to maintain homeostasis, if your pH shifts, you have bicarbonate buffer system, you have a phosphate buffer system, you have proteins that act as a buffer. You'll change your breathing. That's why you start breathing faster when you're jogging, is that you're trying to get more oxygen in your cells, you're trying to get rid of the carbon dioxide. It's your psychological way of trying to maintain that pH. And renal is your kidneys. So your kidneys will also excrete excess. So you have a lot of ways that you try to maintain homeostasis in those cases. So anyway, all right, so that's everything.